Reproducibility. It's pretty much the foundation of good engineering, right? But with LLMs, getting the same result twice can feel like you're chasing a ghost. Today, we are diving deep into LLM non-determinism, not just to talk about it, but to actually defeat it, showing how we can get bit-for-bit identical results every single time.
So let's start with the mystery I'm sure every single one of you has run into. You set temperature to 0. You're telling the model, hey, be deterministic, use greedy sampling, and yet you get different results. Doesn't matter if it's an API or a model running on your own machine. What is actually going on under the hood? Now, the usual suspect that gets trotted out is this idea, the concurrency plus floating point hypothesis. The theory goes that because GPUs do things in parallel, the little math operations can finish in a slightly different order each time. And because of how floating point math works, those tiny differences in order can lead to different final numbers. It sounds super plausible, right? But as we're about to see, it's not the whole story, not even close. All right, let's put on our detective hats and really investigate this. We're going to start by putting the first part of that popular theory to the test, the floating point math itself. This right here is what I like to call the original sin of numerical computing. We all learned in school that A plus B plus C is the same no matter how you group it. But for computers using floating point numbers, that's not true. Because they have finite precision, rounding errors sneak in. If you add a really tiny number to a gigantic number, the tiny number can just get wiped out, completely lost in the rounding. And this is a fantastic, if extreme, example. In that first line, we add 0.1 to a massive number. The 0.1 just gets swallowed by rounding error. So the result is basically 0. But in the second line, we let the two big numbers cancel each other out first. And suddenly, the correct answer, 0.1, is preserved. Same numbers, different order, wildly different results. Okay, so this is the crucial pivot. We've established why a different order gives you a different result, but that doesn't explain non-determinism. The real question is, what is making the order of operations change from one run to the next? The common myth blames random GPU thread scheduling, but what if we test that directly? And spoiler alert, this simple test blows a huge hole in that concurrency theory. We're just running a standard GPU matrix multiplication 1,000 times in a row and checking if the output is bitwise identical every single time. And guess what? It passes. The result is perfectly, absolutely deterministic. So if it's not the parallelism inside the kernel, what else could it be? So why is that torch.mm call so stable? Well, it turns out that modern deep learning libraries are incredibly clever. They go to great lengths to avoid the main source of hardware non-determinism, which is something called atomic adds. Instead of having a bunch of threads race to update a single value, they use structured deterministic methods. And for a typical LLM forward pass, there's just so much parallelism across the batch that they don't even need to use those messy atomics. The culprit isn't inside the kernel's execution. So, if a single kernel execution is deterministic run to run, we need to look higher up the stack. And this brings us to the real culprit. It's a property, or really a lack of one, called batch invariance. Batch invariance is a pretty simple idea. In a perfect world, the math for your single request should be exactly the same, whether it's run by itself in a batch of 1, or if it's run alongside 31 other requests in a batch of 32. But as we're about to see, our highly optimized GPU kernels often break this fundamental assumption. This piece of code right here, this is the smoking gun. We're comparing two things that should be identical. First, a matrix multiplication on just a single row. Second, a matrix multiplication on a big batch where we then just grab the first row of the output. The results should be the same, right? But they are not. And not by a tiny rounding error, by a significant amount. This is definitive proof that the kernel changes its internal math based on the batch size. And here it is, the whole chain of cause and effect. It starts with unpredictable server load. To be efficient, the inference engine dynamically batches requests together. This constantly changing batch size gets fed into GPU kernels that, as we just saw, are not batch invariant. The end result? Your output changes not because of some random race condition, but simply because of who else happened to be in the queue with you. So now that we've found the real root cause, we can actually fix it. This isn't some fundamental law of physics we're up against, it's an engineering problem. And the solution is to engineer our kernels to be batch invariant across the 3 key operations in a transformer: RMS norm, matrix multiplication, and attention. First up, RMS norm. The issue here is that optimized kernels try to be clever. For small batches, they'll split the work across multiple cores just to keep the GPU busy, but that changes the order of additions. The solution is actually pretty simple. We just force the kernel to use the same reduction strategy every single time, even if it's slightly less optimal for tiny batches. Matrix multiplication is a similar story. High-performance libraries will actually switch between different low-level instructions or strategies depending on the exact shape of your matrices to squeeze out every last drop of performance. So the solution is to lock it down. We compile a single fixed kernel configuration and force the system to use that one and only that one, guaranteeing the reduction order never changes.
Attention is definitely the trickiest of the bunch, because here you need invariance not just for batch size, but also for how the sequence is being processed, like a long prefill versus a single decode token. The fix is a bit more nuanced. Instead of splitting the reduction into a fixed number of chunks, we split it into chunks of a fixed size. This clever trick ensures the math for any given token is identical, no matter what else is going on.
Okay, that was a lot of low-level kernel engineering. The big question is, does it actually work? Let's look at the results.
Take a look at this number. We send 1,000 identical requests to a standard, non-deterministic VLLM server with temperature set to 0. Out of 1,000 requests, we got 80 different unique answers. 80! That is a pretty brutal illustration of the problem we're trying to solve. And now, the moment of truth. After enabling our new batch-invariant kernels, 1,000 requests, 1,000 bit-for-bit identical completions, perfect mathematical reproducibility. This is the proof. The theory was right, and the solution works.
Of course, the next question on every engineer's mind is, what's the performance hit? And, there is one. An unoptimized version is about twice as slow, but once you start tuning, like with an improved attention kernel, you can claw a lot of that performance back. It's not free, but it's definitely within a very usable range for many applications. But this isn't just about being neat and tidy for the sake of it. True guaranteed determinism unlocks applications that were basically impossible before, and maybe the most powerful example is true on-policy reinforcement learning. See, in RL, if the model you use to gather data is even a tiny bit numerically different from the model you're training, you're technically off policy, and you have to use all these complex correction algorithms. But with deterministic inference, you can guarantee the sampler and the trainer are bit for bit identical. The statistical distance between them, the KL divergence, is 0. It just simplifies everything and helps you avoid nasty problems like reward collapse. I absolutely love this quote from the source material because it really captures the spirit here. It's so easy to just throw our hands up and say, oh, that's just a weird hardware thing, we can't fix it. But this shows that if you dig in, you can peel back the layers, find the real root cause, and actually engineer a solution. And that's really the thought I want to leave you with. This whole thing started by questioning a piece of conventional wisdom. It really makes you wonder what other issues in our incredibly complex systems, the ones we just write off as bugs or quirks, are actually solvable engineering problems just waiting for someone to ask why one more time.